Okay, good afternoon, everyone, and welcome to this joint session. This session is being hosted by, it's the Distinguished Webinar Series in Artificial Intelligence and Cybersecurity, which is hosted by the Center for Cybersecurity Research. And it's in joint, where today's session is joined with the EECS 500 graduate seminar course. Our presenter today is Professor Sicong Shao, one of our new professors here at the University of North Dakota in the School of Electrical Engineering and Computer Science. And his presentation today is titled Self-Adaptive Anomaly Detection for Cybersecurity Applications. So at this time, I will hand over to Professor Shao, and do enjoy the presentation. Thank you.
Oh, thank you, Avenue. Thank you for your introduction. Hi, everyone. So today, it's my pleasure to give you a presentation. And the title of my presentation today is Self-Adaptive Anomaly Detection for Cybersecurity Applications. So let's get started. So first, the outline. So first, I will introduce the anomaly detection. Share your screen. I didn't share my screen. Okay. Is the screen shared now? Which? Good. We're good. Oh, it's in the right. We're good. Okay, in the right monitor, right? Okay. Okay, so hi everyone. Okay, so the outline. So first, I will talk about anomaly detection, right? Give you an overview of anomaly detection, and also mention several key obstacles, challenges of anomaly detection. Then after that, I will discuss two use cases. The first is multi-level anomaly behavior analysis, which is the anomaly detection-based application-level intrusion detection system in my research. Then after that, I will talk about the tactical cyber immune system, which is a self-adaptive anomaly detection-based host-level intrusion detection system. Okay, so. So first, what are anomalies, right? So basically, anomalies are also referred as outliers, right? Deviant outliers, novelty, exceptions, and in the data mining and the statistical literature. So as you can see here, right, as illustrated in the figure, N1 and N2 are regions consisting of a majority of observations, and hence here, hence it considered as a normal data, right? So those two regions, and whereas the region O3 and the data points O1 and O2 are few data points which are located further away from the majority of data points, and hence are considered as anomalies due to several reasons, right? Such as malicious actions, system problem, right? System fault, or intentional fraud. Okay, so and these anomalies reveal, some interesting insights about the data, and are often convey valuable information about data, right? So therefore, anomaly detection, anomaly detection consider important step in various decision-making system, right? Especially in a cybersecurity system. Okay, so and also usually we can divide anomalies into three different types. First, point anomalies. basically, if an individual data instance, right, a data samples, can be considered as anomalies with respect to the rest of the data, right? Then the instance is termed as a point anomaly. So this is simplest type of anomaly, and it basically focus majority research focusing on the point anomalies. And also there another type called the contextual anomalies. Basically, if a data instance is abnormal in a specific context, right, then it's termed as a contextual anomaly. So, for example, right, as you can see here, so the T2 and the T1, right, actually they have like a similar value, but because they are in the different context, right, due to the different context, and hence this pointer is considered as anomaly. And the third type of anomaly is called the collective anomaly, or you can also call it a group anomaly, right? Basically, if a collection of related data instance is abnormal with respect to the entire data, right? But the value itself does not have to be abnormal. But a group of those collective of those data points, we can consider them as abnormal data sets. We can consider it abnormal, right? Okay, so and due to the increasing demand and the application in broad domains such as risk management, security, financial crime, also like industry security, healthcare security, video surveillance, social network and web security, and especially in a system, software and network security, right? So anomaly detection is playing a very important roles and highlight in various communities, including machine learning and cybersecurity. So a simple problem formulation of anomaly detection, right? As you can see, basically when we given a set of data, right? And potentially also we might have some label, right? But we don't have but it's not a must, right? So, but at least we need to have a set of data points, okay? So, and then we want to find a function identifying the data samples that are significantly deviate from the majority, okay? And basically, so F, right? The task of anomaly detection, we want to find the function F, right? Which is the evaluation function that use anomaly detector to evaluate the anomaly score of sample of the instance or data instance xi, and then we will give a score, anomaly score of this particular specific instance or observations. And basically abnormal sample, right? Abnormal sample of the abnormal sample is the one whose anomaly score exceed or beyond a threshold, right? While this is abnormal sample, right? Basically the anomaly score is beyond your threshold. And also while for the normal sample, right? Usually the anomaly score is is less than a threshold. Okay, so this is a simple formulation of anomaly detection. Okay, yeah, so, and also, of course, we need to find a threshold, right? So, and anomaly detection can mainly divide into, machine learning based approach and some simple statistical based approach. But the most of the anomaly detection algorithm, especially the state-of-art machine learning, anomaly detection algorithm, they are a machine learning based approach. And for machine learning based anomaly detection algorithm, usually we can divide into one class learning based approach, right? And also unsupervised learning based approach, depending on whether you have that Y, right, that label. But if you have also have a label, you can also formulate the anomaly detection as a binary classification and try a binary classify, okay? And for the model, right, in the machine learning based approach, machine learning based anomaly detection approach, we can divide the, based on the complexity of your model, we can divide it into shallow model and a deep model, right? The shallow model usually, it's like a traditional machine learning based approach. For example, like a one class SVM, isolation forest, local outlier factor, those approach, right? And due to the advance of neural network deep learning, right? So basically, the deep learning also currently there are also many deep learning based anomaly detection approach through like a neural network, right? To learn a complicated representation through multiple layers to learn the complicated your data distribution. And also there are some simple statistical approach. For example, like a Z-score based, right? Usually you assume your data distribution follow a Gaussian, right? Then you look at how many deviation, and also like a MED, right? Median absolute deviation approach. They are simple statistical approach. There is no learning, for this approach. And because we are interested in machine learning based anomaly detection algorithm, because they are state of art, and however, most of the machine learning based anomaly detection, they follow the IID assumption, right? Actually, because most of machine learning algorithms, they follow the IID assumption. So same thing. So machine learning based anomaly detection algorithm, most of them, they are also hold the IID assumption. Basically, IID assumption is assume your data distribution, your data is independent and identically distributed, right? So for anomaly detection machine learning algorithm, at least, right, usually you will assume your normal data follow your IID assumption, okay? But the problem is, because the majority of the anomaly detection algorithm, machine learning based, they rely on this assumption. They rely on the data sampled from a fixed probability distribution. However, this assumption is always violated in many real-world applications, which result in the detection performance that are far from optimal or even reliable. So, and the reason why resulting, that IID assumption fails, because, most important reason is because the concept drift, right? Your distribution is changed over time. And because of the concept drift, now your IID assumption fails. And for concept drift, we can usually divide into 3 different types of concept drift, due to the distribution change. So this is for the virtual, we call it a virtual drift. Why? Because as you can see here, right? So the posterior probability here is still remain. By the way, first the concept. Let me give you a definition of what concept drift is. Basically, it means your x and y, your joint probability is not equal over time, changed over time, right? This is the joint probability of your feature space x and your label, your prediction, your label y. Okay, they are joint probability change, and for the virtual drift, right? As you can see, for the virtual drift, actually your posterior probability is still fixed. It still does not change, and also your the probability of x, right? The probability distribution of x changed. So this will result in the joint probability changed. But because of the posterior probability is still fixed, so actually it's not a big issue, right? Because your decision function, your decision boundary will still keep same. And the problem is when you when your posterior probability change, right? And in that case, as you can see here, right? Basically, your decision boundary is completely changed. And if you train a machine learning model using this data, right, and later you do the prediction, your test data, in this follow this distribution, right? As you can imagine, your performance will be, will be very bad. And also, even worse situation is, your distribution, your margin probability, your margin distribution of x, right? The probability distribution of x, and also your posterior probability change. This will make the situation, even worse, right? So and because of those issues, right? We have to handle those concept drift, right? Otherwise, your model, the performance will decrease over time. So this is the first key challenge, right? Key obstacle. The second key obstacle is we call it extreme verification latency problem. So in contrast to conventional machine learning study, right, that focus on learning from a given training data sets, learning from data stream, right, cannot ignore the fact that the incoming data stream can be potentially endless with with huge size and no changes. And so it's impractical to assume you have a infinity, you have enough supplied computational or manpower resource to provide the user the label, right, over time. And such that and also many of the approach for learning in non-stational environments, they assume that the label are available even during the stream, which can give you some feedback, right? But unfortunately, many applications, they do not have that luxury of regularly being provided the label in your non-stational stream. There are many like adaptive learning approach, right? Basically, they need some human feedback, during the stream. Even so when the concept drift happens, they use some like human feedback to give some new label, or even through like active learning, give some new label, right? But actually, in most of the, in many of the applications, especially cybersecurity application, right? When you have to deal with the large scale data stream, you don't have that manpower, that human feedback to give you that label information. Okay. Okay. So now more common, actually a more common learning set is there are limited label data, right? Very limited data for learning, and if the unlabeled data, right, are classified with model, there will be a time of latency between your classification when the true label, when your true feedback become available, and this is known as the problem of verification latency. But in most verification latency situation, actually your labeled data are only available at some initial time, and then only the unlabeled data available in the stream. So this scenario is commonly referred as extreme verification latency. Okay, and which is very common actually in cybersecurity applications, especially in the data stream based. Okay. So now I give you a very high-level introduction of anomaly detection, right? And also mention the two key challenges of anomaly detection. So now I will start talking about my research. Basically, it's focusing on anomaly detection-based intrusion detection system for computer and the software security. So and those two systems, they are anomaly detection-based approach. So the first, I will introduce the MLABA, multi-layer abnormal behavior analysis. Basically, it's anomaly detection-based application level IDS. So we want to learn, the normal behavior of your application and try to identify any abnormal of your application. And also another project. By the way, for the application level IDS, okay, so it's just without it's a anomaly detection based approach without adaptive learning. But for the TCIS, right, because in the TCIS project, it's a self-adaptive. We are monitoring a host environment. It's much more complicated. So we need a more powerful machine learning model can perform self-adaptive to maintain the performance in a more complicated host environment, right? So we for that project, host IDS project, we develop a tactical cyber immune system, which is self-adaptive anomaly detection-based IDS for the host system. So a very simple, a high-level introduction of the IDS. So basically, intrusion detection system, are designed to identify the suspicious and malicious activities. And it can be divided into signature-based detection approach and anomaly detection-based approach. So for the signature-based detection approach, they use fingerprints, right, of no threats to identify them. So once the malware or other malicious content has been identified, a signature is generated and added to your database, right, and to your list used by the IDS. And so solution and as a solution to test, incoming content, and this enable IDS to achieve a high threat detection rate based upon detection of no malicious content, right? However, a signature-based IDS is a problem. As you can see, it's limited to detecting no threats, right? And is blind to let's say a no vulnerability or even 0-day vulnerability. Okay, and for the anomaly detection based IDS, the solution is build a model of the normal behavior of the protected system, and all future behavior is compared to this model, and any anomalies are predicted as potential threats and also generate alerts. And also, as you can see, the advantage of anomaly detection based approach, it can detect the novel or 0-day threats, right? But the difficulty is also, the difficulty of building an accurate the difficult part is how to build an accurate model of normal behavior, right? Means that this system must balance, false positive with false negative. Okay, so I will first, discuss our application level IDS, which is a deep learning based anomaly detection for monitoring a specific application, such as like Google, such as Chrome browser, your web browser, right? Then I will introduce the host level IDS. Okay, the host IDS, basically the host IDS means monitor your overall host system state and may monitor the combined behavior of all your applications running on your computer. Okay, on your, maybe for example your laptop, right, or any of this Windows computer. Okay, so first, MLBA multi-layer abnormal behavior analysis for application. Okay, so the research challenge for traditional application level IDS, it have suffered several problems. So many of them, they are signature based IDS, right? And also many machine learning based IDS, right? They have been proposed with a strong closed set assumption that needs both normal and attack data for training the detection model. For example, like binary classification based model based IDS, right? And also many of the current efforts of application level IDS, they using the single application data source for anomaly detection may not enough for successfully detecting planned and motivated attacks that leverage the vulnerability from multi layers. For example, right, just give you an example. Okay, the malicious behavior of stolen SSH credential from application, right, is hard to identify only from the application data. Okay, but abnormal traffic, right, such as unusual interaction between user and the computer in the network traffic, right, it might expose this malicious activity. So to this end, right, so we propose a multi-layer MLBA, right, feature representation model with anomaly detection, built on the data from multiple sources that collects, the multiple layer data from system, from your application, and also from your network to monitor a specific application for anomaly detection based intrusion detection. Okay, so the research objective, first, we want to design a novel technique that integrates the process layer, system layer, and the network layer to achieve decent application level intrusion detection performance. And also we want to train anomaly detection model, right? Because it's anomaly detection based approach only with normal data. And also we need to implement the proposed technique and conduct a case study on popular applications. So basically, MLBA is a multi-layer abnormal behavior analysis framework for application intrusion detection associated with 3 layers. Okay, and for detect the normal for learning their normal operation, right, and detect any abnormal behavior that might be triggered by the abnormal activities. And it also have a couple of advantages. First, it support the MLB support continuously monitoring, which means it continuously monitor and diagnose the operation of three layers. And we have a three layer future representation model, which can capture a wide spectrum of possible behavior of application by different type of cyberspace footprint. And also it's anomaly detection based, right? It's anomaly detection based approach. It no need to attack data for training. So, because the attack surface, right, of modern application, consists a wide range of components, including logical components, network components, and physical components. So this is why we aim to create application ideas for detecting suspicious activities, using a comprehensive future representation rather than the representation designed to only focus on the application. So this is a high-level structure of the MLB framework. So first, we using the continuously monitoring tool, right? We monitor the cyber infrastructure consisting of system, data, application, and the users. And the cyberspace footprint, which means that is selected measurements, right, from the cyber infrastructure, extract the system footprint, application footprint, and the network footprint. And here the system footprint, application footprint, and the network footprint refer to the selected measurements that can respectively record the system, application, and the network behavior in informative and appropriate, accurate manner. So after that, the footprints of three layers are transformed to a feature vector and combined to form the MLB future representation model, which is used to learn our deep learning based anomaly detection model. Okay. So as you can see here, right, the system layer, basically the system layer, we map the hardware and the physical objects onto the cyberspace through the system footprint that contains such as system-wide measurements. For example, like CPU times, disk usage statistic, right? CPU utilization, memory information. So all of those information, they are system-wide measurements. And the process layer, it maps the target running process using the application footprint, including the process measurements such as the process CPU related measurements, right? For example, the Chrome, how many CPU usage, just for the Chrome, right? Just give you an example. And also the process memory related measurements, and also the process I/O related measurements, something like that. So the network layer will map the data communication using the network I/O measurements from the network footprint. And the richness of those three layer cyberspace footprints, right? From it can capture a wider spectrum of possible behavior of application, right? Since as I just give you an example, right, for that SSH application malicious behavior, since because the application, right, since application level cyber attack, perhaps it can reflect their impact by monitor measurements at each layer rather than just the monitor that application itself, right? Like Chrome, for example, right? It's better you are also monitor like your network traffic, right? Just give example. For example, if your Chrome, the CPU usage is increasing crazy, right? But the network traffic is not increased, then it means actually it might get stuck in some infinity loop, for the Chrome or for the malicious resulted by a malicious behavior. Okay. So on the collected cyber footprints, so now it's the anomaly detection phase of the MLB model, right? So we just mentioned the three-layer feature representation for the MLB. Now here is the anomaly detection phase of MLB. So basically on the collected cyber footprints, right? The objective is extract the features for data mining, right? And extract the features from those 3 layers are concatenated to form our 3-layer feature representation stored in database for training our anomaly detection model. And the machine learning pipeline leverage anomaly detection model for abnormal behavior analysis. The stage for training anomaly detection model, only requires the MLB machine learning pipeline observes the, previous normal behaviors represented by the 3-layer feature representation model. And this allows the anomaly detection model to model normal behavior. And the anomaly detection model is because only trained on normal sample, right? After finish the training stage, the model can distinguish the behavior of normal and abnormal. So the machine learning algorithm here, for example, right? Basically the goal is we want to learn a function, right? Looking for a function that can identify whether your application is normal or abnormal. So the machine learning algorithm we use is a deep learning based approach, which is autoencoder. So actually the capability of autoencoder is able to reconstruct your input on the output in the output layer, right? So this is autoencoder. Usually autoencoder used for like a dimension reduction task, right? But it can also can be used as anomaly detection. So how can we do that? Basically we treat the autoencoder only with the normal data. And remember the goal of the capability of the autoencoder is it's able to reconstruct your input on the output layer, right? So if we treat the autoencoder only with the normal data, and during the training stage, right? So all your parameters, free parameters of your neural network, which is autoencoder, they are all learned from normal data. And after the training complete, right? During the testing stage, during the prediction stage, if there is a normal sample, as the input, right? Because the autoencoder is learned from the normal behavior, from your normal data. So it should able to successfully reconstruct your normal input on the output layer. But if your input is, is abnormal sample, right? Some concept, some instance you never observed during your training stage, then in that case, the autoencoder should not be able to reconstruct in the output layer, right? And as you can see, so now we can use the reconstruct error as the anomaly score, to measure whether this specific sample is normal or abnormal, right? If it's a normal sample, your reconstruction error will be small, right? And if it's an abnormal sample, because it cannot successfully reconstruct your input in the output layer, right? You should have a large reconstruction error, and then we just need to find a good threshold, right? And so in this way we can detect, we can perform anomaly detection. Okay. And the goal is to learning that function, right? Neural network. Then we conducting our experiments. So basically, for the normal behavior, right? We just we collect the data. We collect, if I remember correctly, we collect more than 10 hours data from normal user behavior. Like for example, when they and we conduct the experiments on 4 application software. They are Firefox, Chrome, Opera, right? And also software development tool, Ruby. So we collect the normal data, right? How users use them in a normal way. And then we also create several attack scenario to collect the abnormal behavior. Okay, so and the attack here we use the fork bomb attack, infinity loop attack, infinity array attack, and also ransomware attack. And also, brute force password correcting attack, and the rainbow target, and the rainbow attack. Okay, and we also, in order to compare with our autoencoder based approach, right? Basically here we use advanced autoencoder, which is denoising autoencoder, right? So the difference between DAE, denoising autoencoder, with standard autoencoder is, we add some noisy into your training data, but the goal is still reconstruct your original input. So because of that, right, your autoencoder should be more robust, right? Because even you add some noise in your input, right, it's still able to reconstruct, your original sample. So it should be more robust than the standard autoencoder. Okay, so we use a denoisy autoencoder, and we compared with some shallow-based anomaly detection approach, such as isolation forest, one-class SVM, local outlier factor, and also E. Okay, so so as you can see, right? So these two, and also we evaluate. We use the AUC raw curve and the precision recall curve to evaluate the performance of the different anomaly detection model. And for the future representation stage, right? All of them, they are using the MLBA future representation model. And as you can see, right, most of anomaly detection algorithm, right, they achieve good results, which validating the effectiveness of the MLBA future representation model. But as you can see, right, the denoisy autoencoder is still, obviously better than other approach, right? Better than other approach. Basically, we repeated the experiments 15 times, right? Because we also want to consider the stability of your of the different approach, right? So as you can see, so we also have a standard deviation in the results. So so as you can see, right, in most cases, okay, the autoencoder, the denoisy autoencoder, it achieve better performance in regarding the AUC score, right? AUC score, and also the average precision, right? Basically, the AUC score, right, it summarizes the entire location of your raw curve, and the average precision, it can summarize your precision recall curve. Okay, so, and those figures, they present the visualization of the mean raw curve and the mean precision recall curve for all the anomaly detection approach, right, on Firefox and the Chrome. And the standard deviation information, as you can see, right, is also included in this curve. So the overall, right, the mean raw curve and the mean PR curve of denoisy autoencoder based anomaly detection algorithm, it cover other anomaly detectors, showing a better performance. And for the Opera and the Ruby, right, as you can see, the denoisy autoencoder based approach, right, it still roughly cover other anomaly detector. Okay, and however, also you can maybe you can notice that the LOF, right, local outlier factor based anomaly detection algorithm, they also shows a good performance, but the problem, it also shows a higher standard deviation, okay, of true positive rate and the precision, right? Especially when the especially in this figure, right, as you can see here, especially in this figure, as you can see, the local outlier factor, they show a high, standard deviation, which is not good, which means it's not very stable. Okay, so yeah, so this is become making its stability of prediction somewhat unsatisfied compared with the noisy autoencoder. Okay, now we will talk about the host level anomaly detection based intrusion detection system, right? Remember, for the MLBA, right, the task is we are building an application level IDS. The task is relative compared with the host level. It's relatively simple, right? Because you are just train a model, for example, for Chrome, right, or for your Firefox. It's for a specific application for your browser, right? But when it comes to the host level IDS, we are monitoring your entire host system. For example, right, your laptop might running more than 100 different applications. Okay, but we still want to create IDS anomaly detection model to detect any abnormal behavior of some host system, right? Especially some host system in data center, right? It's a important thing we want to secure. Okay, so as I mentioned, right, the the research challenges as as cyberspace complexity increase, right? So modeling and detecting cyber attack and the threats for host system become very challenging, right? Due to the complexity and the big data stream, your stream data needed to be analyzed in real time. And also, the whole actually securing host system in a complex, interactive, and a dynamic environment, is urgent because it's a non-stational. Actually, it's a non-stational environment, right? Due to much more complicated concept of your host system. And also in most scenario of host IDS, right, the labeled data are only available at some initial time, and then only the unlabeled data available in the stream, right? Which actually is it's EVL I just mentioned in the introduction, right? Extreme verification latency environment, right? For example, if I want to protect a laptop, right, and my mom is using that laptop, it's difficult to ask my mom to give some feedback, right? Whether your machine learning prediction is whether it's wrong or correct, right? Or even in some data center, in many host system in data center, because due to the huge stream, accumulated over time in the data stream, right? It's really difficult to ask even a security expert in a data center to label some, some data, right? So you might only have some initial labeling data, right? But it's really difficult to ask them to, provide the, your feedback, after in the stream prediction stage, right? Due to that, your data accumulate over time, and it's endless of data. Okay, so it need some approach which can do some self-adaptive learning to handle the anomaly detection task in complicated environment. So the research objective of TCIS tactical cyber immune system is first, right? We want to developing a host intrusion detection system, which it needed to be researched for accurately identify self and defending against non-self threats for the entire for your whole host system, right? And also, as I mentioned, due to the challenge, right? So we needed to develop a self-adaptive anomaly detection system for host level intrusion detection to overcome the security deficiencies of the current computing system in a non-stational environment, right? And the most probably, lacking human feedback, right, due to the limitation of the manpower. Okay. And also the reason why we call it the tactical cyber immune system, because you just think about it, right? For example, let's say a woman touches the host stove, right? But thanks to her nervous system, right, she snatched her hand away before she gets gets too hurt, right? So, and also like another example, a virus, right, enters your body, but your immune system fends off the invader before it can cause too much damage, right? So it's like an anomaly detection. You are creating an anomaly detection based, immune system, right, to protect you. So we call it we use this fancy name called tactical cyber immune system. Okay, so and also we needed to we needed to develop the host system, right, which can learn in a dynamic and a changing environment, right, such that the learning can be done with high accuracy and detect the change in a complicated environment and lack human feedback. So the TCIS basically is a high-level overview. It's a self-adaptive anomaly detection-based host level intrusion detection system. Okay, so the goal of the task of this system is to classify your host normal operations and detecting any abnormal behaviors that might be triggered by a malicious activity. And also the implemented system can detect a cyber attack and insider threats in real-time data in your stream data, right? And identify any abnormal behavior or concept drift, and then automatically adapt the model according to your identification. And it enables intrusion detection on modern complicated host system. And it have a couple of features. Still, it's continuously monitoring and diagnose your operation of your host machine 24 hours, 7 days. And also we create a host behavior feature representation model. Basically, we use similar feature representation model compared with the MLB, but it have some different. I will mention in later slides. It also can capture a wider spectrum of possible behavior of the host by different type of footprints. And also it's anomaly detection based approach, which means we don't need attack data for training. And also it's a self-adaptive learning. Basically, it's a fully autonomous and automatically adapt the decision model in the open and involving non-stational environment, especially for the host environment, which we cannot get the human feedback, or even you can get even some feedback, right, in a very, very long latency. Okay. So this is a high-level architecture of our framework. First, we monitoring the host data, and then we continually filter the useful cyber footprints, right? Then we do some feature engineering to extract some features. Okay, now as you can see, the difference here is for the application level ideas, right? Basically, the features we are monitoring is much less than the host, right? Because the host, we are monitoring maybe more than 100 applications running in a single time, running simultaneously, right? So we need some, instead of directly use the MLB feature representation model, right? We need to, because now we are considered 100 application, okay? They are in a very high dimensionality. So we need to use some dimension reduction technique or even feature selection technique, right, to reduce the dimensionality in order to avoid the curse of dimensionality, in a machine learning problem. Okay, so and also remember, because we are using the anomaly detection based approach without the observing, without using the attack data, right? So we also need some unsupervised feature selection algorithm which can handle do the feature selection only based on normal data. And then after that, right, after we get the reduced feature representation model, it's more informative, but much lower dimensionality. Then we use that feature representation model to train our anomaly detection model. It's still deep learning based approach, autoencoder based approach, but with a more advanced setting. We will use the LSTM, basically LSTM based anomaly detection model as an anomaly detector. But the concept is very similar. It's just instead of looking at the point, right, we are observing your sequential information to reconstruct the sequential information to detect your abnormal or normal behavior. And before we deploy the model, into the stream environment for real-time analysis, right, we also need to do some validation. And after we deploy the model, in the stream environment, in order to handle the non-stational and extreme verification latency environment of the most host system, right? They suffered. So we needed to, we developed a self-adaptive learning module for anomaly detection in order to maintain the performance of anomaly detection performance over time. Okay, so for the feature representation model, right, we are using the MLB feature representation model as an initial feature representation. But since it's in a very high dimensionality, we need to reduce the dimensionality in order to extract a more informative but the lower dimension feature representation model for learning the anomaly detection model. So the technique here we are using is Laplacian score. So basically, the Laplacian score is an unsupervised feature selection algorithm. It's based on Laplacian eigenmaps and locality preserving projection. So and also it used Laplacian matrix for graph of graph. It used Laplacian matrix of graph to store neighborhood information of data. And then for each features, right, we will calculate its Laplacian score. And to reflect its locality preserving power and to perform the feature selection, unsupervised feature selection. So, and for the anomaly detector, now as you can see, we are still using the autoencoder based approach right here. We are still trying to reconstruct something. We learn something normal in the training stage And due to all the data is normal, so all the free parameter, right, of your neural network is learned from the normal data. But during the test stage, right, if you know something normal, right, because you already observed a similar concept, you should be able to reconstruct with a lower reconstruction error. But something, if your input is something abnormal, right? So because it's very different compared with your observation you learned during the training stage, right? So you cannot successfully reconstruct, then it will result in a large reconstruction error. But as you can see, right, because now we are monitoring the host system, it's a much more complicated environment, right? So we increase the model complexity, and we try to learn the sequential information, which can give us more information, capture more information of your entire host system, right? And so we use the LSTM layer, as the encoder and used as for the encoder and the decoder instead of the standard dense layer of the standard neural network. Because the LSTM layer, right, it can encode in your sequential information instead of your point anomalies. As I mentioned, right, in the first slides, the abnormal behavior, it can divide into point anomalies and also collective anomalies, right? So collective anomalies basically is very similar to sequential information. It gives you more information, right? Okay, so but the concept is very similar, right? Just instead of reconstructing point, now you try to reconstruct the sequence information due to the complicated environment of the host system. So this is our self-adaptive anomaly detection framework. So as you can see here, the anomaly detection model, by the way, because recall that, right, the anomaly detection model performance will decrease, right, if we ignore the concept-driven problem, right, in the host environment which is not suitable for our task. So it's crucial, it's crucial to adapt the data distribution change in the stream, in the prediction phase, right, especially when your stream accumulate over time, and train a more robust anomaly detection model. So in this project, right, we design approach that use the concept-driven detector to run together with the LSTM autoencoder. Then we will incremental update the autoencoder whenever the drift is 5 minutes. Okay. speed up. Okay, sorry. So then we will basically we design approach, right, that use concept-driven detector run together with autoencoder, and anytime the concept-driven detector distribution change, right, so we will incrementally update the autoencoder. And the autoencoder will be trained on the normal data, right, with a reduced feature representation in the training module by our feature selection algorithm. And then the pre-trained autoencoder will classify the data after it's executed in the test data, right? And the concept drift detector run with autoencoder and use the output from the autoencoder, which is a reconstruct error, right, or anomaly score, as the input. And the retraining function, the incremental learning function will be invoked whenever the drift detector detects the drift point, detect the distribution change, right? And the important thing here, and the sample with the lower reconstruct error will be used to tune the autoencoder, right, to do the incremental learning for self-adaptive learning, right? The reason why we use lower reconstruct error to tune the autoencoder, because we don't want to use some abnormal sample, right? Some potential abnormal malicious sample to tune the autoencoder, because the goal is here we are doing the one class learning and based anomaly detection, right? We just want to learn the normal behavior. Okay. So as you can see, right, the key point here is we need a good concept-driven detection algorithm, and it needs to be unsupervised, right? Because most of concept detection algorithms still, you need some label information, but so we want to avoid them, and we use unsupervised concept-driven detection algorithm, which is KS2 sample test. So in the concept-driven detection phase, right, we use the KS2 sample for drift detection, and which requires we create a two data window, right, recording the reconstruction error observations. Basically, we use the reconstruction error. Basically, it can represent your distribution summarize your distribution of your whole system, right? Kind of summarize your whole distribution of your system. So we use the concept-driven detection to monitor your risk construction error, also known, in this context, also known as anomaly score. And we create a two window, right? With one window recording the latest concept, and another window will record the earlier concept, and then we will compare the CDF, right, the distribution inside those two windows. And the KS2 sample test is a statistical test, with no assumption of underlying data distribution, which just compare your CDF, right, between your two different distribution. And with a significant level of alpha, right, we can determine whether we can reject the null hypothesis that the reconstruction error observation in data window in these two data window originate from the same distribution. Okay, so so here the null hypothesis here, right, is the distribution is not changed, and the alternative hypothesis here is the distribution is changed. So anytime we beyond the threshold, right? So we will we will reject the null hypothesis and accept the alternative hypothesis, which means your distribution is changed, and then we will invoke the the autoencoder to do the incremental learning. Okay, and the good thing, the important thing why we need that concept-driven detection algorithm, because you don't want to do the incremental learning at every time step, right? Because remember, the host system you face with huge data sets. Okay, for example, when we implement the system, like 1 hour, we might for a single computer we might receive like several gigabytes data. Okay, so it's really difficult to do incremental learning at every time step, every second, right? So we need that concept drift to detect when only we want to do the self-adaptive learning when the drift detection is detected, right? So here the KS2 sample testing is very important for this purpose. So here is some results, for the self-adaptive anomaly detection based TCS, right? So basically, as you can see, so here is the results when the TCS anomaly detection model without that self-adaptive learning capability. Now, as you can see here, right, so the upper figure, basically, it's the anomaly score, or also known as reconstruction error in this context, right? It shows the reconstruction error and the anomaly score over time, right? Over time, and the lower figure, it shows the prediction, your prediction against ground truth label. Okay, so as you can see, in the lower figure, right, because the prediction is represented as a blue color, and the label is represented by and the label is red, right? So which means when it's if they completely overlapped, which means your accuracy 100%. Okay, but if there are a huge non-overlap, right, which means your accuracy is very low, which is not good. Okay, so now, as you can see, right, when without the self-adaptive learning capability, as you can see, during the normal stage here, right, during the normal stage, I need a laser point here. During the normal stage here, right, as you can see, it's still good, right? Most of the time they are overlapped. But when the attack happened here, okay, basically we launched more than, I think we launched around 13 different cyber attack. Okay, most of them they are host level attack, and also some of them they are insider threats. They are different attack here. We have around like 13 different attack. Okay, now as you can see, in the normal operation stage, right, the system is still okay, but during the after the attack appeared, right, so it started confused between the normal and abnormal behavior. Okay, so there are a lot of false positive here, as you can see, false positive and false positive, right? So after attack launched, right, so it's almost cannot distinguish between normal and abnormal. And here basically we monitor data over 10 hours here. Okay, so and after we include that self-adaptive learning, now as you can see, right, it's improved a lot, right? Because now as you can see, most of the time they are highly overlapped. Even the attack happened, even here we launched 13 different attack, right? it's still able to successfully distinguish between the normal and the abnormal behavior. And as you can see, due to this high overlap. And also another difference, as you can see, right, when we, without the self-adaptive learning, right, we only have a one threshold, right, which means although, by the way, although here we still do the concept drift detection, but the difference is when even the concept drift detector, right, we didn't do any updating. The model is not updated, right? So basically the vertical red line means, you know, some drift point detected by the concept drift detector, but we didn't invoke the autoencoder for incremental learning, right? So as you can see here, it's really do a bad job, you know, after your attack happens. Okay, so and after we turn on the self-adaptive learning capability, as you can see, right, we have a lot of threshold because the model is doing some self-adaptive learning, right? And when it finishes, when it performing self-adaptive learning, the thread also needed to update, right? So as you can see, so instead of so anytime when we detect the drift, the model will performing self-adaptive incremental learning, you know, to catch up the latest concept. Now, as you can see, right, so the performance is much better, you know, due to this high overlap between the between your prediction and your ground truth label. And also we implemented the we implemented the TCS data pipeline and for handling large-scale data, non-stational stream, class imbalance, and also the feedback latency, right? Even no feedback. And we implemented by leveraging Kafka as a streaming messaging platform and using Spark TensorFlow, right? And also MapR event to achieve the end-to-end pipeline, which can handle this capability, right? Large-scale data, non-stational stream, class imbalance, and feedback latency. Okay, so conclusion. So first, today we introduced the anomaly detection concept and some of key challenges. Then after that, we propose a novel MLB framework, right, that integrates the process system and the network layer, multi-layer, tree layer to achieve the descent application level anomaly detection based intrusion detection results. And then after that, right, we built the TCS, which is a more advanced host level IDS, right, which is a self-adaptive anomaly detection based host IDS to classify your computing system's self and defend against any non-self threat, right? And it can detect the normal and abnormal behavior and also can detect the concept drift in non-stational stream data and then autonomously adapt the model according to the identification, even without human feedback, right? Okay, so basically we introduce you the concept of anomaly and show you several use cases, how to do the anomaly detection for the IDS for cybersecurity application and the more advanced version, how to do the self-adaptive anomaly detection for a complicated environment, for a more practical environment. Okay, sorry. Okay, so it takes too much time. So thank you. For any questions?
Thank you, Dr. Sicong. We're glad to have you contribute to our webinar series. Right now, I'd like to encourage any of our online participants to post their questions in the Q&A. I see we already have one question.
Oh, yeah.
First question is, how are you setting and determining the level of threshold for the encoding model to distinguish between normal and abnormal?
Right. Actually, okay, it's a good question, right? There are multiple ways to do that. One effective way I can tell is for example, right? For example, let's assume we are using that autoencoder based approach. So we have, we can plot all the anomaly score distribution, and then we after, because we do many experiments and we observe that most of the time, almost all the time, right, it follows Gaussian-like distribution. Then in this way, basically, we just set the threshold, we can treat like how many, deviation from the mean, right? Usually you can set like 3 deviation plus your mean. So, and also a very important thing, we need to use that validation data sets to do that plot the anomaly score distribution, right? And then we calculate the threshold based on like kind of this score based approach, right? We assume your anomaly score follow the Gaussian distribution, and then we treat like any points, their reconstruction error, if it beyond the mean plus like 2 or 3 standard deviation, we treat it as abnormal. And you can also do some like cross validation. For example, you splitting your training data, right, to the 10 different folds. Every time you treat your autoencoder on the 9 folds and calculate that threshold on that 1 fold, right? And then you repeat like 10 times, and you use some like you average the threshold among those results. Yeah.
Okay, thank you. We have another question. What portions of what you presented, if any, are open source? If so, where can we access some of the code?
Yeah, okay, yeah, that's really a good question. Actually, this system, because we developed for Navy and the Army, right? And so basically, currently we didn't publish the code, but because the Army, Navy, they are currently, for example, the TCS Army, they are deploying this system in their center, I think in Washington somewhere in their lab, they are testing them. So we need to get their approval. So if they agree, so yeah, in the future, definitely we will, publish the code. Yeah.
Thank you, Dr. for your presentation. I have one question. All these, we've been speaking about concept stress. This is all going to be uncertain. And then we talk about there's a lot of unrelated data in the streaming environment. Correct? And the machine learning models have not seen such signatures of what's going to come next in the streaming environment. And so if so, while we have all these models out there, right? I think how do we see as we go forward in handling a very large streaming environment, yet you need to use memory and resource constraint aware machine learning algorithms, because all the training set that we talk about is going to take a lot of data.
Right. Sure.
But we want to this offline and online training is great, but when you want to really handle the streaming environment, you probably want to look at very memory constrained
right
approaches, right?
Right.
What are the thought process on that?
Yeah, that's a great question, and actually I'm also exploring this problem, because this is really an important problem, to implementing a successful large scale anomaly detection system. So currently, one way we are considering, we try to make the algorithm like one pass learning. We kind of add some one-pass learning concept to our system. Basically, the difference of one-pass learning means all the stream data sample you only will observe it one time and then throw it. So basically, as you can see, right? So it won't queue your memory, because every time after you observe that point, you throw it. So, but how to effectively and effectively use that one-pass data, right? It's a challenge. So currently, I'm working on this direction also.
Thank you. I think in the interest of time, I think what we're going to do is we'll appreciate Dr. Sicong for his lecture.
Yeah.
And this webinar is also available as part of Center for Cybersecurity Research. Any questions do you guys have here before we conclude? Any other final questions from here? No?
There's one more on the chat.
Okay.
You mentioned that the autoencoder can distinguish between normal and malicious samples, right?
Right.
So if you're feeding only normal in there, what if there's a data poisoning attack? Can it distinguish samples generated due to that attack?
What if what?
Data poisoning attack?
Oh, data poisoning attack. Okay, so yeah, currently we are just we assume there is no adversary learning in that environment. Yeah, but this is one direction. In the future we can consider if there's some adversary exist in your security in your monitoring environment, right? Then yeah, this will create a headache. Okay, yeah. Yeah. Also, one important thing I forgot to mention that currently I'm a recruiting student before the conference. Yeah, currently I'm a recruiting student. This is my email address. So if you are interested in working with me, just send me an email. Okay, so we can have a talk. Stop by my office. And my research, as you can see, right, basically is focused on intersection of machine learning and cybersecurity, especially for applying machine learning for addressing like a system and software security and digital forensic. So research task. Yeah. Okay, I continue. Yeah. James, any other question? Okay.
Yeah, just one more, and I think in the interest of time, this will be the last one. Is there a published paper or report that has more explanation on the anomaly classification in your
It's a great
IDS?
question. Actually, currently we have we submit a paper and it currently is under review. Because actually, as you can see, right, the goal of this project actually because it's funded by Army and it's SBIR project, so it's more focused on the the commercialized and prototype implementation. In order to continue the next phase. So at that time when we working on this project, we put all the effort on the prototype, system implementation. So this is why currently the paper is still not published, okay, but it's under review currently. So, yeah.
Great. Let's thank Dr. Sicong for his time. And as part of your contribution for the webinar, we'll get a nice plaque from our Center for Cybersecurity. Thank you so much for your time today.
Thank you, Prakash.
I appreciate for being here.
Yeah.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you, Prakash.
Thanks, Dr. Sicong.
Yeah.
You can hand the